Hey, in this video, we are talking about characters and C strings in C++ programming, and this covers sections 10.1 to 10.3 in the Gaddis textbook. So we've talked about strings before. We all know that strings are made up of a bunch of characters, basically, and in this chapter, we're going to dig into a lot more detail about exactly how they're structured and what you can do with them and so forth. But in addition to that, we are also using this as a first example of taking a fundamental data type like character, putting a bunch of them together and making some more interesting, more complex data structure out of that. That's going to be a recurring theme for the rest of the course, actually. So this is actually not a bad starting place to think about how one does that in C++ programming. Okay, so first of all, let's be very clear that in C++ there are at least two different varieties of strings. There's C strings, which is what you would have to do in the older C language, and then there's new style, I would say, C++ string objects. And one of the things about C++ is it adds more features and it adds more features over time, which is great, but as a C++ programmer, you have to be aware of all of those features because they might show up in a particular code base. So let's think about that. In C++, you've got C strings, and they're not really anything special. All they are is an array of characters. That's it. I mean, that's the whole idea of a string after all. So just literally an array of characters. But at the end of that array, you've got to have a byte holding the number 0, which we refer to as being null terminated. And that is how C or C++ recognizes that it's reached the end of a string. On the other hand, you've got C++ string objects, which are an object-oriented class, and we'll talk more about what that means later, with extra safety and extra functionality automatically built in. And you really ought to know about both of these things. Now, in this video and the next, we're mostly going to focus on the traditional C string here. Why are we going to do that? Well, that's actually how string literals, the things in double quotes in your code, are actually stored in memory. That is how command line arguments come into your main function from the command line, actually, like that. That's how binary files can be written in a very efficient and very easy manner, which we'll talk about in chapter 12. So there's a bunch of really fundamental things built into C and C++ that assume you're using C strings, very simple character arrays. Now, are you going to be using C strings every day of your life? Well, probably not. I mean, if you have C++ strings available, you probably ought to use that more often, frankly. Like I say, it's got this, extra functionality and extra safety built in. So maybe you actually ought to use those most of the time. But on the day when you needed to dig into lower level functionality, you do need to know about C strings. So that's what we're going to focus on here. And again, it's a good, very basic example of building more complex data structures out of something very simple. Section 10.7, the last section in the book, gives information about C++ strings, and I'll let you read that on your own. Okay, so first of all, strings are built out of characters, so let's just talk about characters for a second. There are a bunch of functions in C++, and we have just inherited these from the C language, so you're kind of learning two languages at once now, for testing what type of character you're dealing with. And these are all in the CC type header file. So the C language character type library. And here's a bunch of options, okay? So each of these would take one parameter, which is a character, and it would return true or false if this is that kind of character you're talking about. So there's isAlpha, which checks on, is this an alphabetic character, a letter in the English alphabet, of course. Could be uppercase, could be lowercase. Either of those things would return true. There's this function isAlnum, which means is it alphabetic or numeric, right? Any letter or digit. There's the isDigit function. Is it one of the digits 0 through 9 for this character? There's a function isLower that reports on, is this a lowercase alphabetic character? So lowercase ABC, it returns true. Uppercase ABC, it returns false. Punctuation, parentheses, asterisk, it would return false for all that stuff. There's also, a little bit lower in this table here, there's also isUpper, which obviously does the opposite thing. Reports true if you're dealing with an uppercase character and returns false for any other type of character. Those are the ones you're probably going to use most often. Somewhat more exotic stuff. There's isPrint for is this a printable character, something you would actually see, as opposed to an enter or a horizontal tab or something like that you wouldn't actually see. There's is punctuation that reports true for commas and question marks and quotes and asterisks and stuff like that. And then there's also the is space function, which reports true if this is white space. And remember, that includes an actual space, a tab, or the enter key. Okay, so that's all different types of white space, and that's what the is space is hunting for. Okay, so keep that in mind. We're at the point in the course where I would not expect anybody to just flat out memorize any of this stuff, but you ought to know that it exists. And on the day when you're writing a program where this comes in play, you can look it up. And you know that you can test for different categories of characters pretty easily with these functions. Okay, what else? So occasionally it's useful to convert character cases, right, from lowercase to uppercase or vice versa. Very easy to do. C++ has functions for converting a character between cases. Again, this is in the same library, so you'd have to include the CC type header file again. So here's your two functions. There's a function toUpper. It takes one single character parameter, and if it's a lowercase character, it returns one character, then it would return the uppercase version of that character. For any other type of input, it just returns back the exact same thing you sent in. Okay, and then of course there's toLower, takes in one character. For most stuff, it just returns the exact same thing, but if you pass in an uppercase character, it sends back for the return the lowercase version of it. Okay, so pretty much like that. Keep in mind, this is not changing the original argument. So whatever you passed in is not being changed, but it is reporting the upper or lowercase version, if available, as a return value. One example where you might want to do this is in program 10.3 in the book, and I'm just going to kind of highlight the part that's interesting, is you have one of these big do-while loops. There's a process happening, and then at the end, you ask the user, do you want to calculate another one of these averages or tax rates or something like that? And the user types in y or n for yes or no. Or there's this sin into the go again character, presumably. I cut out, all the actual processing interesting stuff in this do while loop. You can see there's a big gap from line 20 to 27. I cut out all that stuff. And then how the do while loop is actually going to make that decision. In the past, maybe in the distant past, we to handle the fact that the user could type in either upper or lowercase y to indicate yes. I mean, they're probably going to type in lowercase y most of the time, but if they have the caps lock key on, maybe it'll come in as an uppercase y. We ought to be able to accept either one of those things. And in the past, what we did is we used an or operator there. And we would have done while go again is equal to capital Y, or go again is equal to lowercase y, which is a little bit of typing, basically. So a slightly shorter way of doing that is you could just check, take go again, pass it through the toUpper function, and if at that point, if it's either version of the y, it's going to come back as capital Y. So you could do toUpper, go again, and check and see if that's capital Y, and that'll actually catch both cases. All right, it's saving you a tiny little bit of typing, but that might look nicer in your code, might be more readable, so you might do that. And again, get a little bit of time back from typing that. And then in addition, I suppose, if you change the response that you're looking for, whereas previously you'd have to go change, like maybe I'm going to do the thing if you type Q now. Previously, you'd have to change both the uppercase letter and the lowercase letter, and here you just have to change one thing. Okay, so again, we like short, and that would give you some benefits there. Does not change the original thing, just returns a version that is uppercase. I'll say, other cases where you could use this would be if you want a string comparison function. Normally everything is case sensitive. Uppercase is counted as different from lowercase. If you wanted a function that compares strings in a case insensitive fashion, where you don't care if you're dealing with uppercase or lowercase, you could use this same function to compare one character at a time, right? I wouldn't change the incoming strings, I would just compare one character at a time and use the toUpper function as I did it. So some nice options there. Okay, so that's the story of characters, right? That's just our building block work. So now we're going to start putting them together or see how they get put together in C strings specifically. And this is review. We talked about this, I think, in chapter 2 of the course, actually, chapter 2 or 3. So C strings are just a sequence of characters stored in adjacent memory locations and terminated by the null character, which is to say ASCII value 0. It's actually a number 0 in the last byte. So, that's what it is. It's an array of characters, basically. So as an example, the string hi there, and if you write that string literal in your code, that's got 9 visible characters, right? HI 1, 2, 3, 4, 5, 6, 7, 8, 9 up the exclamation mark. But it's going to take 10 bytes to store that in memory. And you can see that laid out here. So 1 byte for the capital H, 1 byte for the lowercase I, 1 byte for the space, THERE exclamation mark, and then that's how you write null terminator. That is the escape code for the number 0, stored as a character. So it could be a little, keep track of that difference. I would say the string has 9 characters, but it does take 10 bytes there, so be a little bit careful about that. And we have seen this previously in the course, so that's the story of C strings. It's pretty simple like that. You could take all this and you could look up in the ASCII table in the appendix and see exactly what number is really being stored, but that 1 at the end, well, that's the number 0. Okay, so you can, again, thinking about C strings, originally from the C language, you can just make a character array and use that for string storage. So here I am declaring a size for what's going to be my string, a constant integer size marked as 20, and I'm just declaring a character array called city that's going to store some kind of city name. I could initialize that if I wanted to. I could write equals string literal in quotes, right? And it would totally know what to do with that to put it into that character array. Make sure you leave room for that null byte at the end. Kind of like that's a buffer overflow if you fail to do that, which is of course dangerous. We've done this before. We've seen this in a lab in chapter 9. I think that was lab 9.2. So we've seen this at least once before. And then having had that, the SYN object, the SYN extractor, knows how to deal with that. You can totally write a statement that does SYN right arrow into city here, into a character array. And the SYN extractor totally knows how to take a bunch of characters and put them one after the other in your array. That absolutely works. However, couple limitations to that. Remember, the way that the SYN extractor works is it stops at the next white space. Therefore, you couldn't get a space into your string just using the SYN extractor. For example, this would work perfectly fine if the user wanted to enter Philadelphia or Seattle, but it wouldn't work if they wanted to put in New York City because it's got spaces in it. And in addition, the SYN extractor doesn't do any check to see if there's enough space. So if someone types in a very, very, very long city name that's bigger than the space for this array, you've got a buffer overflow situation. And the SYN will actually put all those characters one after the other, run right past the end of the array, smash over whatever variables are stored in memory after that. And, among other things, maybe your program's going to crash, but that's a hacking vulnerability. That right there is the primary way that hackers take control of C and C++ programs, is looking for a non-checked string input right there. So you really don't want that. A better option for input containing white space and to control the amount of input is to use the syn.getLine function. And that'll allow you to specify exactly how much space you're working with, and it will also get white spaces. Let's take a look at that. So here is program 10.5 that demonstrates the syn.getLine function. That's actually sitting on line 14 here, right? We make a character array on line 7 and 8. We set the size to 80, and on line 8, we're declaring a character array called line. As a little aside, 80 is a pretty common size for one line in a code base. And for example, in Dev C++, the IDE that we use, the default right margin size is located at the 80th character. I think in Dev C++ that's under Tools, Editor Options, Right Margin. You can click it on and you'll see this line about really the point where you shouldn't write a longer line. And you can set that to any number you want, but by default it's 80 because that's what most programmers expect actually. So a pretty good example of that here. And then we have a count that's going to be used for a loop counter, of course. prompt the user, please enter a sentence of no more than size -1 characters. And I usually ask my students, why do you think that size -1 is there? And of course, the answer is to make room for the null terminator, right? If I have an 80 character array, I can only store a string with 79 characters in it because I got to use the last one for the null terminator. So there's line 14 with the sin.getLine function passing in the character array, that's line, where you're going to store some stuff, and also a number for the size that you are using for your buffer. So standard, I'm passing an array into a function in C++. You need 2 parameters, and here's the array, and here's the size, and that's what's happening with sin.getLine. And when that happens, the user can type some stuff in, and it reads everything up to the enter key, including spaces, including tabs. And if they type in more stuff than 80 here, it just gets cut off so you don't have a buffer overflow. And in this case, they do something kind of interesting. It says we're just going to display the input back out, but we do it 1 character at a time, which isn't really going to look any different on the screen. But it says the sentence you entered is, and how we're going to print that out. I mean, it would be, you could just do count arrow line would work, okay? But just as a little experiment here, what this example does is we are going to print 1 character line, print the first character, and to control this, you're going to have to use a while loop looking for that null terminator. So it starts off and, well, if line 0, right, that was the first character, if it's not the null terminator, then just go and print that first character, right, line bracket 0, and then increment count up to 1. You come back. As long as line number 1 is not 0, this is a legitimate visible character, and we'll just go print line character index 1 and increment the count. And you keep going, and you keep print character number 2 and number 3 and number 4, and at some point you run into that null terminator, the 0 byte, that's the end of the string, and then it stops printing, of course. So we couldn't use a for loop here because offhand you don't know how long a C string is. There's this sentinel value, I would say, this null terminator at the end, and you just have to treat 1 character at a time looking for the null terminator. So you do have to use a while loop for the way that C strings are organized. You know, there are other languages, actually, for what it's worth, Pascal language strings were set up where the first byte was a number for how long it is. And so in a Pascal string, if I want to do that, I could use a for loop. But if you have a marker at the end, you've got to use a while loop as you search for that. So if you run program 10.5, there's a little example down here where it runs, and the program would ask, as you see up on line 12, enter a sentence of no more than 79 characters, and the user presumably has typed in C++ is challenging but fun, enter. And it's going to print the sentence you entered is C++ is challenging but fun. But the interesting thing is that was printed 1 character at a time using this while loop. Again, if you did this for real, you could just do count arrow line, and it would handle that properly. But you ought to know that that's possible to handle 1 character at a time. And we'll need to do that sometimes. Probably the next assignment, frankly. Okay, so that's a pretty good introduction to how C strings are organized, and we saw the options in both C and C++, they are the same, for checking what type of character you're dealing with, for converting lowercase to uppercase and vice versa, if that's useful, thought about exactly how C strings are constructed, and the fact that you can just make a simple character array, and you can use it with sin, and you can use it with count. Even better is the sin.getLine function to be safe about the sizing, and all that stuff is pretty important. So for my students, the next time we're in person, we would do this lab here in lab 10. It's called American Equities, where it's simulating a financial services company. And in this very simple example, you have to type in a password that has, I think it's like, it must have 4 letters and it must have exactly 3 digits or something like that. So there are these functions. There's one function to count the number of digits in the C string. And there's one function to count the number of letters, the number of alphabetic characters in the C string. And the interesting thing that I really like about this lab is those counting functions don't use array syntax, as in the example we just saw, right? That print 1 character at a time was using array syntax to do it. These functions don't do that. They use pointer syntax. Is you have a pointer aimed at the first character, and then what they do is they increment the pointer to aim at the second character and the third character using pointer arithmetic. And I feel like it's a really interesting example because a lot of programmers, when they're dealing with that kind of low-level issue of dealing with individual characters in a string, in this case to count them, they're probably going to revert to pointer syntax. You're going to start thinking about pointers, and among the advantages actually is you wind up saving a variable. You don't need a counter variable like you do in the for loop. So it might actually be a little bit shorter and might actually save some memory, a tiny little bit of memory, but it's going to look very different. So I like to, in this lab, take kind of a long look at exactly what that function's like so that we can deal with that or possibly write low-level functions like that ourselves in the future, or maybe an assembly language class that comes later on. So if you do have access to the labs in the Gaddis textbook, I do recommend look at this lab. I think it's a great example. Next time we come back, we're going to be looking at more C string library functions. This video is kind of, one character at a time. Next video, we're going to look at some functions that can just deal with a whole string for us at once. As far as C strings go, from both the C and the C++ language. So a little bit more powerful next time, and I'll see you then for that.